The meeting is now in session.
Welcome. Thank you for joining us today for the webcast titled Introduction to EMIEMC Challenges and Their Solutions. This is the third presentation in the webcast series titled Overcome High-Speed Digital Design Challenges, brought to you by Agilent ESOF. I'm your moderator, Carmina, and I have a few short announcements before we begin. This webcast is designed to be interactive between you and our presenter. To participate in our question and answer session, just enter your question anytime in the chat window. Be sure to address your questions to all panelists. Use this by clicking on the pull-down menu in the chat window and selecting all panelists. Our presenter will make every effort to answer your questions live, so I do apologize in advance if we don't get to yours. But don't worry, because if we do run out of time, our presenter will respond to the remaining questions via email. After the webcast, we will ask you to fill out a short survey. The survey will automatically open up at the conclusion of the webcast. By submitting the survey, you'll be providing us with valuable information on how we can offer you more and better webcasts in the future. Now let's move on to the presentation. Joining us today will be Dr. Hany Fahmy, high-speed digital application expert in Agilent ESOF. Welcome, Hany. You now have the floor.
Thank you, Carmina. So welcome, guys, to our webcast today. Introduction to Introduction to EMIEMC challenges and their solution. By the way, it wasn't a mistake. I think it's really a black magic. As everybody knows in today's industry, EMIEMC is really a black magic that our EMI engineers get into this closed chamber called the anechoic chamber, 3 meter, 5 meter, 10 meter, and suddenly comes out of the chamber with a solution that is high cost, that usually interrupts the project, usually causes big headache to the project management due to loss of gross margin, because suddenly they came out and they requested either shielded connector, they requested chokes on parallel lanes like HDMI lanes, and they actually request connector really expensive. Anyway, what we're trying to do today is to go ahead and try to understand the phenomena of radiation and how we can use virtual lab using both simulations and hardware measurements to help us identify the problem. This actually is attributed not only myself, but also to Professor David Pessour from Killian University, Chuck Jackson, Charles Chu Chen Wang from NVIDIA Corporation, Amlak from Avago. So if we go to the next page, what is today's solution? Yes, as I mentioned a moment ago, it is a Band-Aid. The EMI engineer gets out from this closed chamber, and then it's dark as well. So anyway, it gets out of the chamber with this Band-Aid solution. This Band-Aid solution, as I mentioned, it's trying to stop the bleeding of emission that found some emission problem at some harmonics. But the problem is that this Band-Aid, because it happens at the last part of design cycle, it happens during the time where the product must go to production and to final production as soon as possible. No time to be left to be heard by the EMI engineer. Therefore, that solution becomes non-optimal, doesn't always work. It works with some mainstream systems, but not be working across all the corners, across, let's say, all the PVT corners of the chip. It's also costly, as I mentioned. Like to look at like a shielded connector, usually costs 15 cents more on the PCB. So such of Band-Aid solution, we're trying to limit it. And by the way, I wasn't joking when I mentioned Band-Aid. If you look here, this is a GPU card, and we'll actually see the story in a few slides that the card was bleeding in the coupling to the nearby Ethernet card. And one of the solutions was indeed to put a copper Band-Aid to prevent that bleeding of emission from that card. As you can see from here, the copper Band-Aid is connected with screws to the ground planes. It's very well connected to the connectors so that it would provide a good shielding. But who knows, does this work? Who knows that this solution works? We go to the chamber, we have to design the solution, go to the chamber, and try to do the far field measurements. There is actually a very similar Band-Aid to this one. If you guys take a look at it, they're very similar together. This is indeed an NEC R4N suppression material. Yes, it's very effective for suppression the emission of cards. By the way, this is the same card, but this is another solution. But how to know that which solution works? Can our virtual simulation lab help us to arrive at a solution remedy to this billing problem fast enough without actually causing this loss of millions of dollars that are wasted and waiting for products to get certified? Can we do that? Let's see. If we go to the next page, everybody knows that the EMI problem is very complicated. Why? Because we can start from the chip level. The chip has I/Os, it has a core, it has power pins. The I/Os usually they're not 100% perfect. That we're talking about differential lanes such as HDMI. These can have rise-fall mismatch, and they can easily inject common mode noise. Now this common mode noise would propagate into the PCB and would fly to the cable. So these I/Os can inject noise, and then there is also the power pins of the chip. These can also inject noise into the power delivery network. And then badly routed traces can generate EMI. We use to generate guidelines for signal integrity and power integrity. But do we have guidelines really for EMI? I know that are cases that are badly routed from EMI perspective. I think we are hoping that the simulation can help us to find. High-speed connectors and cables can amplify the EMI problem. And therefore, they can get the common mode noise running on these connectors and cables, and these becoming non-intended radiators. Now the problem starts becoming amplified. This is a near-field scanning of GPU board. And here is the IC injecting this common mode noise to the PCB. And because of this low-cost board, as we're going to see in a few slides, we can see that the common mode travels to the PCB to the connectors. So when it arrives at the connectors, it created hotspots, that the common mode. Now, the connectors are not shielded well, whether they are grounded well to the PCB or whether they are connected with the good gaskets to the chassis, this common mode noise can easily fly through the cable and, as I mentioned, becomes intentional antennas. Here you go. What we're going to do is to go ahead from the source, minimize the IC noise emission, then to the package, then to the PCB, then to the trying to reduce the effect of emission from the connectors and cables, and then we'll do the whole overall system. And we're hoping actually that simulation plus hardware measurements, they both can help us achieve this goal. So let's see the different mechanisms of noise propagation. With noise source, let's say the I/O buffers of an HDMI interface. These should be purely differential, but everybody knows they are not. And for, as I mentioned, they can inject noise to the PCB. This noise can travel inside the PCB through the traces as conductive noise. These can reach, as an example, it can be a connector. So this can be the connector and the cable. And they actually fly away and becomes non-intentional radiators, as I mentioned. It's one possible mechanism. The possible mechanism is that the noise source itself can start radiating. Now it can start radiating coupled field to that equipment device or exposed device. As an example, I look at one example where we have a GPU card calling noise to the nearby Ethernet card. And the Ethernet card now starts carrying that common mode noise, and common mode noise flies through the Ethernet cable and starts radiating. The third mechanism is that, again, the noise source, how now it's going to be coupled to the equipment or exposed device. You guys have any idea? It can be conductive noise, then translated into radiation noise. It doesn't have to be all conductive or all radiation. It can be partially conductive and then change into radiation, then coupled to the equipment or device exposed to noise. What is the fourth now? Can you guess it? Yes, the noise source will start radiating first, and this radiation starts coupled to the conductive noise, and then it reaches the receiver and causes the emission type of a problem. So these are type of the four common way of mechanism of noise propagation, and what we're trying to do is to understand how is the noise generated, how we can interrupt this path and prevent the emission from becoming a problem for our products. So, difference of emission. We know that the chip with the bolts landing at, let's say, at the locations on the PCB, or this is actually a package where we do have a big pump here. Now the IOs of buffers can inject signal, as we know, and when they inject the signal, these signals, let's say, they can excite slots, or actually, if these signals passes the slots, now they can actually excite radiation in free space. So it's one type of emission which is called trace emission. There is another type of emission, as you know, the wave propagation of signal is not only traveling on the trace, but actually from electromagnetics, the wave is guided between the metal of the trace and the reference plane. Therefore, there is a return current that exists on the reference plane. Again, for that return current, if it passes by slots as an example, if it actually have return path discontinuity as you see, it can cause also radiation problem. This is the fourth type. Fourth type, every chip has power pins. As power pins can be of different rails. Let's say the core noise, let's say the memory noise, the PCI Express, whatever interfaces exist on the chip. These power pins can actually inject noise into the PCB. And this noise, as a wave, it can be propagating outside, away from the pins of the power pins of the chip. And if we don't have the capability of the suppression, that we suppress the propagation of this noise, then this noise is going to propagate on the PCB and on the metals, on the planes. And these planes would act as a good radiator. The fourth type, everybody knows that there is a large number of interfaces using connectors. Here's an example, a EMI interface, where we know that there can be common mode, again injected from the chip, now travels to the connector, and if that connector is not well grounded to the PCB, then as we know, it can carry the common mode, and going through the cable, and the cable now, the HDMI cables becomes good, effective antennas. And everybody knew very well in the anechoic chamber, if we remove the HDMI cables up and down, we can really see very fast change of the emission, and that means that these cables can carry good kind of common mode noise. So, how can we now solve these problems? We are introducing the Virtual-EMI lab. For pre-tape-out, we are suggesting to use a set of simulation tools. Everybody knows that there is no single method can do it all. We use different techniques based on the problem in hand. We can use frequency domain electromagnetic solvers. We can use time domain electromagnetic solvers. As we're going to be exposed to the examples in this material, we're going to try to find more about the best solving technique. We're trying with these simulation tools to find out the best routing and guiding guidelines, EMI guidelines, similar to the signal integrity and power integrity guidelines. For post-out, here we recommended combined measurement and simulation together. We go chamber with the product, we found the frequency of violation, then with near field scanning, try to find the hotspots and the location, then for the simulations, with again here, we're trying to find the best simulation technique, whether it's moment method, finite element, finite difference time domain, try to find the best technique to actually correlate the hotspots together. And once we correlate the hotspots, then now we can do a what-if analysis to try to mitigate the risk of emission. So this is all theoretical, but we need to see something. We need to see how this is actually applied to realistic examples. I mentioned here we optimize the routing of the traces through developing EMI guidelines. And then for the post-layout, we use both the measurements and the simulation to guide us to the best risk mitigation technique for EMI. So as I mentioned, this is all theoretical, but I really want to see something practical. Let's see here a problem of radiated emission on packages due to return path discontinuity. If you guys follow our webcasts, actually have a previous webcast that was talking specifically about such return path discontinuity on memory controller packages. Here we're showing what is the problem. The problem is we have a package, we have here a die pump, and we have data nets for GR3 routed, and this is a byte lane. That's a cookie cutter of the package. It's an 8-layer package. These traces are routed, sandwiching between the two ground planes, and then as they move from the top to the bottom to pick up the bolts from the die pump bolts, definitely they need to go through, plated through holes. And now as you can see that once the traces was on the top of the package, return current were referencing or were existing on plane 1. Once they go to the bottom of the package to pick up the bolts, now the reference current or the return current becoming plane 2. Now there is no good path between connection of the ground plane, which is the green plane, and the yellow plane here. Now they're going to exist something return path discontinuity. Now we actually before showed the impact of signal integrity and power integrity of that return path, but today we would like to complete the whole picture and show the 3 impacts, SI, PI, and EMI all together. Now, here actually we're using the method of moments. Why are we using the method of moments? It's the best technique for multi-layered structures. The moment method would compute the dielectric green function analytically inside each substrate layer. We discretize the metals and the voids. We account for the surface electric current on each metal. We account for the magnetic current on each void. Then after computing these currents, let's say here from here up to 20 gigahertz, because the bandwidth of DDR3 running at this data rate, which is 1.3 gigabit per second, would need us to solve up to 20 gigahertz. However, you guys are free to go as high as you wish based on the interface that you are solving. So when you have such type of moment method solution of the surface electric current and magnetic current, we can now compute the far field from these computed surface currents, electric and magnetic. And the moment method works great for such type of a problem. So let's look at the problem in more close look. Here's the die pump on the top of the package, and they actually go from layer 1 with micro vias to 3, where this biplane is routed. This biplane is sandwiched between 2 ground planes, the red plane and the yellow plane. It's a routed as symmetric strip line with equidistant to the ground plane, the red one, and the yellow plane together. So it's running as symmetric strip line. It's running most of the routing on the top of the package, and as I mentioned, reference to the red and yellow planes. Now they go pick up the volts of the package, so they have to go through PTHs or plated through holes. And let's see how the story continues. It goes at this point here, through plated through holes, then it goes to layer 6, the red plane here, and then continue routing as coplanar with white, in order to go down again with micro vias to pick up the bolts of the package. You can see the referencing changed. It changed from referencing this yellow plane on the top of the package, and also the plane on top of that, now to the plane on top of this red one. Or there is a return path discontinuity. What the impact of it on signal integrity, on path integrity, on EMI, that's something we need to investigate. If you look at the top view of the routing here, and this is routing reference plane, so this is looking at the yellow reference plane on the top of the package. We can see here are the plated through hole for the signal vias. These are 11 bits of data nets. But can we leave that yellow plane and the ground plane on the bottom of the package without connecting together? Here you can see 15 ground PTHs, 1, 2, 3, 4, 5, 6, and you can count up to 15 for these stitching vias connecting the top ground plane to the bottom ground plane. But the question, how do you know that this is an enough number? So let's do the exercise in a different way. Let's reduce that number to 3 only. So I kept only 1, 2, 3 stitchings. And let's see the impact from SI, PI, and EMI perspective. So you can see from here, the 2 planes, one on the top and one on the bottom, they're connected with 15 ground PTHs here. But on the right-hand side, we're only connected through 3 ground PTHs. What will be the impact? This comparison of the current on one of the ground planes, the top ground plane. This is the ground PTH. Here, you can, in moment method, you can control any number of traces of the S parameter solution. You can control how many signals are excited. Here I excited one signal just for simplicity. You see that most of the current on the top ground plane is confined under the trace. You see that the problem happens with 3 ground PTHs. Look here, there is more wider spread of the current on the trace. So maybe this region you can see also more spread as well, but like it's mostly actually spreaded in the near end region of the die pump. So you can see wider physical spread of the return current of the ground reference planes when you don't have enough number of stitching vias. So that's the impact on the surface current. So if you look at the size of the spread compared to the size of the spread for 3 ground PTH, you can see that this one is higher. And that also causes larger crosstalk in the near end. If you look at our previous webcast, you guys actually can look at it. You can ask it on demand. You can see that we have shown that there is a 10 dB extra crosstalk between the case of 3 ground PTH and 15 ground PTHs. So, what about the impact on the I diagram for this memory system? This package is driving 2 SODIMMs per channel at 2.33 gigabit per second. This is the I diagram we obtained at the DRAM devices with 2 SODIMM per channel. This is top for data, bottom for strobe. And the case for 3 ground PTH, the top is again for data and the bottom for strobe. Now, you can monitor some change in the eye opening, but you won't be able to judge it visually. Therefore, the best thing is to use our compliance, which is our compliance mainly mechanism inside EDS, can easily compute the setup and hold parameters of the eye mask that is defined by JEDEC. Out of that compliance, DDR3 compliance mechanism that we use inside ADS schematic, when you run this convolution engine, now you find that we have worst case setup margin 95 picoseconds. Here you can find it drops to 55 picoseconds. Why I'm making it red? It's still positive. Yes, it's still positive, and we will make 40 picosecond of margin only due to the lack of ground PTHs or due to the reduction of ground PTHs. As we mentioned, the end crosstalk increased by 10 dB. That reflects into 40 picosecond loss of margin of the eye. However, the eye opening is still positive. So we have a problem for signal integrity. Now, if we get here, when we're going to move here into a video, to actually the comparison of the surface current, and we're going to share that with you. So I'm going to show you how the surface currents look like between the case of 15 ground PTHs to 3 ground PTHs. And once we run the movie, we can have a better feeling about why the near-end crosstalk increases, and also we can have a better feeling about why the I lost 40 picoseconds. Until now, we only take a look at the impact of eye opening and near-end crosstalk. But don't forget that today we're talking mainly about EMI, so therefore we need to look at the EMI effect. So let me get full screen so that you can better see it, and I'll get the movie running in a sec so that now you can see the impact of that ground return current. So the question is, can we relate this problem to emission problem and this problem of a lack of return path with the reduction of ground stitching from 15 down to 3 can cause this EMI problem? That's something we're just going to take a look in a sec. So in a sec, we'll get the screen on. And here, and we'll take a look at, so run the movie. this package represents the original one with 15 gram PTHs, and I just run the movie, and I see that now how the current is flowing under the trace that I'm exciting. And I'm going to see and compare to the case of gram PTHs only. So, I'm running for the surface current that is on that reference ground plane on the top of the package. Look at how the wave is propagating from the dye pump to the PTH region. And you can definitely that still the return current is confined under the trace. It doesn't spread widely around the trace. When good number of stitching, again, how good is good, that's something to be simulated in order to know that this 15 actually would be enough for this 11 nets. Even more cost reduction packages like 6 layers, and so the problem becomes even more pronounced and needs simulation to be able to have a good risk assessment. So, as I mentioned here, this is the flow of the currents under the trace, and then we're going to move here from 15 gram PTHs to of gram PTHs. See the spread of the current. Try to imagine more spread of the currents, of the return current on that ground plane, can result in more emission or not? What do I think? So this is of 3 gram PTHs. Let's try a movie, see the wave propagation, which is presented by that surface current on the reference plane. You can definitely hear more wider spread. You can see also more wider spread here on these decoupling caps. Surface current on the ground plane, ground plane, has been widely spread. I think that this can cause emission problem. How can we derive a risk assessment about the impact of that widespread of return current due to only using 3 gram PTHs, which people may think that that may be enough on 11 nets as long as it's close to the signal transitions. But definitely much wider spread of return current, especially on the near end. So let's answer that question. Can we know this widespread will cause us an emission problem? Here we do. I just mentioned the answer in the beginning of the material. Once we computed using the moment method, the surface current that exists on ovals and voids, we can run a very simple post-processing script to compute the far field as the PCB becoming an antenna. And that's true. You can compute the far field from the surface current that the moment method computed. That's the far field radiation pattern of this 15 gram PTHs. And now that's the far field computed for 3 gram PTHs. But this post-processing takes very short time to compute because it does merely compute, as I mentioned, the far field radiation out of each element of surface current existing. But I mean, it's like the eye diagrams. Can I decide that which one is better, which one is worse? It's very hard to decide just visually. For we need to compute the antenna parameters. One important antenna parameter is the antenna gain. And we see from here that the 3 gram PTH actually causes more 8 dB antenna gain, which means that our PCB, unfortunately, becomes better antenna by 8 dB. The total radiated power, which is of the antenna parameters, range from 40 microwatts of the 3 gram PTH to 200 microwatts, almost 6x increase in the total radiation power. Maximum intensity, 5 per steradian, 5 microwatt per steradian, for 15 gram PTH, become 40 microwatt per steradian, which is 8x increase in the maximum intensity. The angle of maximum radiation, which is 160 degrees for the 15 gram PTH, becomes 40 degrees for the case of 3 gram PTH. Not a major change, almost 20 degrees change in the theta, which is measured from the z-axis. However, the most dominant impact here is that the antenna gain becomes 8 dB more, total power 6x, the maximum intensity 8x, which definitely can give us an emission problem. Now, can give the designer a good tool to really judge between how they can trade off between the cost and the performance. We really want to reduce the number of layers or reduce the number of stitching. You need to do simulations, not only to look at the risk assessment for signal integrity, looking at the eye diagram, but actually you need also to look at the radiation fields. What impact the radiation fields? In the problem, we're still positive in terms of eye opening at 1.3 transfer per second. But for emission, we are 8 more in terms of antenna gain. As I mentioned, 6x in terms of total radiated power. So now, assume that your chip don't have spectrum. Means that we have a problem. Or other way around, let's assume that you want actually to reduce the cost by reducing number of layers and number of stitching. Then we have to make sure that we have PLLs that exist on the clock so that we can enable spectrum once we are forced for it. Because most probably with such type of trade-off, one that it's important to include a spectrum capability, because most probably with trade-off, nothing comes for free. If you reduce the cost by reducing number of layers or number of stitching, not only enough to look at the SIPI perspective, we have also to look at the impact of EMI so that we have a good decision making whether we need to have spectrum enabling capability on our chips or not. And that's also additional silicon cost that exists today. And therefore, the designer can have the complete picture of trade-off between the different parameters of the system. Now, let's take a look at another type of a problem now exists on the PCBs. And the low layer count PCBs or 4-layer PCB, and this is actually type of emission from the address command. Oh, wait a second, I never heard before about emission from address command. Yeah, actually it can happen. At the time, everybody knows that emission can happen from the data bus. However, this time, the problem came at 1/4 the frequency of the memory clock. So it went at integral multiple of the memory clock so that we can be suspicious about the clocks or the data. This was 1/4 the memory clock frequency that led us to the address command. And the problem happened in the 3-meter chamber at 1.6 gigahertz. How do you know that it's the address command problem? How can we find out the root cause of the problem? How can we solve it? The first thing we need to do is to correlate the near field scanning at 1.6 gigahertz. And here we found a hotspot on the bottom of the card. So this is a 4-layer card. And found a hotspot. Let's try to run the momentum simulations, microwave mode at 1.6 gigahertz. And these are the address nets. The problem that happened here is that some address nets go down on the bottom, that reference to a small patch of a power plane, and go back to the top. And actually, nobody knows that this power patch is going to cause a hotspot. Now, we were able to correlate between the simulation and the near field scan, the location of the hotspot. But tell me how these address nets are the cause of the problem. Now, we're going to do something in the virtual world that can be done in the real life. Can anybody in the lab can turn on some address nets and turn off these ones here on the bottom? Unfortunately not. However, in the simulation field, yes, we can actually turn off these address nets and compute the antenna gain and the radiation fields. And we can turn them on and compute the far field radiation and compare and see that major radiation happens because of these address nets. It's only some address nets, they go out on the board and they're referencing this patch antenna. This is EMScan tablet that you can actually put your board on top of it, and then has loop antennas to get you this picture of near field scanning in order to correlate with your simulations here. So now, the root cause of the problem is that some address nets, they fan out from the bolts of the package. They go down, reference a small patch antenna, and they go back again. So why did the designer did that? He couldn't fit enough real estate on this 4-layer board, so that's why he has to do this trick. However, nobody do that. When he do that, then by exciting lambda by 8 patch antenna at 1.6 gigahertz, and that causes emission problem. So what the remedy? The remedy, and you can do that through the simulation as well, is that instead of you go through a lambda by 8 patch, actually you continue with very large patch, which is much larger patch here, that continue referencing these address nets on the bottom of the card. So instead of going top, bottom, and then top again, now we actually continue on one side, which don't create lambda by 8 patch antenna. Now, how do you know that this stuff can give you the correct answer? But I will never claim that you can get dB to dB or picosecond to picosecond or millivolt to millivolt correlation to lab data. It's to mainly emission type of chamber data. However, we can get the trend of the improvement from the simulation here. Simulation can show you that such type of routing can have much better improved radiation pattern compared to lambda by 8 patch case in the previous pages. And the chamber data confirmed at least 16 dB improvement. The second example is NDS emission, again due to the case of low-cost PCBs. Here we have a GPU card is installed neighbor to an Ethernet card. The problem that happened here is that there is emission coupling between our GPU card to the Ethernet card, such as the Ethernet cable carries 770 megahertz common mode noise. And this can be seen by very heightened emission at 770 megahertz, and also you can detect the 770 megahertz component on the Ethernet cable. What is the solution? What is better? We have here traces on the bottom of the card, that is HDMI traces, routed to 2 connectors. So these are the traces on the bottom of the card. One solution came that why not putting a copper band-aid, which is very well grounded to the PCB ground and very well connected to the connectors here. It's one solution, which is maybe work, may not work. The other solution is to use suppression material. What is the difference between these two? The assumption here is that the coupling happens as capacitive coupling between this card, between the emission of the common mode noise from these traces to the nearby Ethernet card. And here, the assumption is that the coupling is inductive. But I know that which one is more efficient before manufacturing these two solutions and spending of time and effort to arrive at a solution space. Now, we can do that easily on the simulator. There's a stripped-down version of the card, so I removed actually the planes on the momentum simulation, microwave mode. I added here a metal shield connected with ground PTHs, and then computed the radiation field and compared it to the original case without the metal shield. Actually, I found that no major change of radiation field. Total power increased slightly, which tells me that actually metal shield is not doing any good. And then again becomes slightly worse. So that metal shield is not really a good solution. We can actually try this for in suppression material. You can get the electrical parameters from the data sheet. Again, you see suppression material, which is one of the suppression materials. Run the simulation, put the radiation field, and compute it and compare it to the original problem. You can get total power dropped by 50%, the antenna dropped by 3 dB, which tells you that the suppression material is indeed a better solution space. Now, here's the original radiation pattern. And now, this is with the suppression material, and you can see that on the bottom of the card, this half apple becomes much smaller than this one. Here with the metal field, almost no change. So therefore, if you really go to the near field scanning, this is the card, the original card. The chip emits common mode noise. Passes through the traces on the bottom of the card. The common mode appears as hotspots at the connector. You put the suppression material, you can find that the same actually common mode noise exists, however, completely damping the common mode noise propagation So it's filtering in the path of the noise coupling mechanism from the source to the receiver, as you have seen in the beginning of the pages. Let's take a closer look at the EM scan. This is the original case, where the chip emitting common mode noise travels through the connectors, creating hotspots at the connector. This is the second case of putting a band-aid, which is the suppression material. And we can see that the same common mode noise exists. But now it is damply traveled. It will able to damp the noise propagation from the source to the connectors. And therefore, it will actually reduce the total emission of the problem. Now, this is not enough, definitely, for EMI. We have to go to the meter chamber with that setting and have to measure the radiation fields and compare the original case with the suppression case. And you really find that it does help the suppression material and not the metallic copper band-aid. Now, sometimes, by the way, the remedy was, one of them was definitely adding the suppression material, but it's more costly. Sometimes, and this is the part of the experience of the EMI engineers, sometimes we have actually to reduce the emission from the receiver side by using a shielded connector instead of actually using non-shielded RJ45 connector on the Ethernet cord. You're kind of like, immuning the receiving antenna. PCB emission, another type of emission problem that everybody faces due to the power delivery noise. The system, as we know that, it's very complicated. We have a chassis of a computer. We have GPU card here connected to connectors that, let's say, go with cables. And they have a package of the GPU and then heatsink. And we know that actually that this package has power pins. And they can easily inject noise on the PCB. And now this can radiate into free space. Besides the noise, they can travel through the cable. So let's take this as a chip that power pins. And let's take this example here of a memory interface. We have dynamic current that's merely taken from the power pins, or the power pins would actually take dynamic current, which causes very fast dynamic current based on the activity of the chip. And this is connected to the receiver, which is here the DRAM devices. And they're both connected through a power delivery that exists on the GPU card. And the question is, how this current profile that existing on the power delivery pins of the chip can impact the emission problem. So the question is, we have measured this current profile on the power pins, and this is the power spectral density. Major harmonics at 0.5 and 1 gigahertz. Now, can this current profile that existing at the power pins, now can it cause noise propagation to the PCB, and this PCB works as a good radiator and can cause this emission problem? Know that. And it's the best technique to solve this problem. Now, this is a wide band phenomena. We're intending here to use the finite difference time domain technique instead of actually using the frequency domain technique. So here we're using the finite difference time domain to do the following. We have time domain current profile. We use it as is, injected into the FDDT analysis and compute radiation fields. This is our board 6-layer GPU card, where this is the pins of the chip, and we are injecting the noise of the current profile at the power pins of the chip. So this is power to ground connection of the different locations of the chip, and we are actually trying to make an assessment about the decoupling gaps that exist under the GPU. In the past, how do you do this, guys? We go to the chamber, we off the card, we unsolder these decoupling caps, we try another ones, we go back again to the chamber, and then try to measure the new radiation fields. And this is becoming very tedious, shooting in the dark. Instead of doing that, we can measure the current profile on the power pins, inject the actual measured current profile for maximum activity of the chip, make an assessment in a virtual lab through the simulations of finite difference time domain, and find out the most critical decoupling caps that can solve the problem. This is the far field radiation at 0.5 gigahertz with the critical decoupling caps, and this is without the critical decoupling caps. You can see that the radiation field is definitely it's much stronger without the critical decaps. This at 1 gigahertz, the radiation pattern changes, but then phenomena happens that we were able to identify the importance of the onboard decoupling in reducing not only the peak-to-peak noise, low-frequency noise exists on the PCB for the power delivery network, but also be able to be effective in reducing the emission and the radiation fields. Here's the current density that exists. This is the case without decoupling caps, and you can see that noise is propagating very well away from the pins of the power pins of the chip. Here you can see that the decoupling caps were able to dampen the noise propagation away from the power pins. So what is the benefit of the PC caps? We'll show a new method. Measure the current profile on the power pins of your chip. Put it into find a difference time domain, and then start measuring the PCB impact of decoupling on the SSO noise emission or the high frequency noise emission or emission due to your current profile. The current profile doesn't need only to be for memory as in this example. It can be also for, let's say, for your core noise or for other type of interfaces. The last example we're going to take a look at is connector cable emission. The problem we have a PCB with HDMI interface and have a connector with a connector mate, and you can get the model of the connector from different vendors of the connector companies. Here, we're going to actually solve the problem of PCB plus connector together. We have HDMI lanes are routed on inner layer, and here we have a chip injecting common mode noise due to rise-fall mismatch that exists on the different differential lanes of HDMI, and then going through the connector, and it travels to the cable. The cable here is represented by a certain load impedance at the connector mate. But you can see it's very important to make an assessment about the importance of grounding of the connector. When the grounding of the chassis and the grounding of the bracket is actually connected to the ground of the PCB. And really want to find out a solution better than our black magic solution, which is finding, let's say, putting chokes on the HDMI lane. So, we want to find out from here. We don't want them out of the chamber with shielded connector or chokes or just copper tape under the connector. We want to really use the engine of simulation to inject the common mode noise on the chip, that how it travels to the connector and how the connector grounding becomes an important parameter to prevent the common mode from radiation. So here actually this solved on find a difference time domain within a couple of hours if you use it on GPU acceleration. So this is the case of no copper tape under the connector. This is the case of a copper tape under the connector, and you're trying to compare in between. You have to see that what is the impact of the copper tape. The blue here is the impact of the copper tape radiation pattern relative to the red one, which is no copper tape. You can see 5 dB reduction of emission in the direction of the chassis, and that was the original problem. So the copper tape under the connector is better grounding of the connector, can do the job very well. Our conclusion is EMI lab becomes today a must for speed of light products so that your product won't be sitting waiting for EMI compliance. Radiated conducted emission, we have seen problems of packages radiating due to return path discontinuity. PCBs low cost 1-4 layers. We have seen problem of radiation from traces by address command. We have seen TMDS emission, and we have a method for these. We have seen noise emission, and we have used finite difference time domain. We have seen emission of a PCB plus connector. We have used also finite difference time domain, especially on the problem when it has PCB plus connector or a wideband phenomena such as the noise emission problem. And then we actually wish you guys to order our trial version for ADS and with our product today. I mentioned a couple of EM solvers that you need for different type of problems, like I've shown here the moment method. Also use the finite difference time domain as I've shown in 2 examples, like PCB plus connector or wideband noise phenomena. You can connect all these together in the ADS schematic and then transient convolution to complete the full picture of assessment between SI, PI, and EMI. Thank you, guys.
So in a moment, we'll begin today's question and answer segment. Remember to complete the survey that will automatically launch at the end of the webcast. And as I mentioned at the beginning, by submitting this survey, you'll be providing us with valuable information on how we can offer you more and better webcasts in the future. So please take a moment to do that at the end of the webcast. Now the question and answer portion of the event. As a reminder, if you have a question, simply type your question in the chat window and select all panelists in the drop-down menu. We'll answer everyone's questions live, but if we run out of time, we'll respond to any questions via email. So Hany, here's your first question from Emmanuel. What type of frequency dependency is considered for the PCB materials?
On the moment method, actually, we have the Drexler-Svensson type of formula that can be assumed for the frequency or the frequency dependency of the PCB material. So that's actually very effective, working very well effective for the PCB material.
Thank you. This question is coming from Annalise. Is ODB++ the only import format? Can you import, for example, PAD's binary format?
Yeah.
So actually,
go ahead, Hany. Sorry.
Not really. Go ahead.
I can answer that one. I'm Colin Warwick here. I was in the chat today. Yeah, the ODB++ from Mentor products we can import directly into ADS. If you have a very large ODB++ file, we recommend a third-party tool, a preprocessor called NetX. Yes, we'll put it in a link in the webcast notes. It's from Artwork Conversion Software. Useful if you have very large ODB++ files. We don't support PAD's binary format. It's a proprietary format of Mentor, and they don't publish the spec of that one.
And again, that's Dr. Colin Warwick, our other high-speed digital application expert. Thank you, Colin. Here's a question from Marcus. Can you give us some guidance as to when to use method of moments versus FEM versus FDTD?
Actually, a very nice slide that Dr. Colin shared it with you guys in his last webcast. But just briefly, moment method works great for PCs and packages when you have multi-layered structures. That includes the traces, the voids, the it's very, very effective in that direction. And again, we have first to answer the question whether we're solving in the frequency domain when you have a narrowband solution, depending also on the high Q of the poles and so forth and the zeros. But moment method works very well for packages and PCBs. Now, if you look at the example that I've shown, and let's have a PCB plus connector, then actually we're encouraging to use the finite difference time domain for that type of structure. That is very large structure, and it's very big, and also it can run very fast on the GPU for acceleration. Now, finite difference time domain as well, or time domain EM techniques in general, they're better to be used with wideband phenomena, as I also showed for the SSOI type of emission type of a problem.
Okay, great, thank you. Here's a question from Stephen. I think it's actually a question. I'd like to reverse the flow, design critical nets in ADS, then export Allegro. Can I do that?
Yes, it's certainly possible to export. You can draw critical nets with ADS layout and do EM solve on them, and you can export them in a variety of formats like DXF, Gerber drill, ODB++, IFF is our proprietary format, IGES. But that's a kind of usual flow because we usually want to use the constraint-based layout in the enterprise board tool like Allegro or Expedition, whatever. Integrating artwork with that constraint-based are usually quite key. So generally people use it to alter the constraint and edit the kind of golden copy of the artwork in Allegro. Now, Hany, what would you think about reverse? Do you ever see that people exporting from ADS layout into an enterprise board tool like Allegro? Have you ever tried that, Hany?
Yes, Colin?
I just think in principle you can export artwork out of ADS layout into Allegro using Gerber drill or ODB++ or something. But is
you mean annotation top of the backwards flows, that right? I didn't read actually. Yeah, because usually we generate from this simulations design guidelines similar to our SIE or PI guidelines, and then again, yes, you can. I think most probably you can. That's what I heard, but I didn't try it myself, really, Colin.
Yeah, I hear what you're saying. I agree. Yeah. Okay. Good.
Sure. Actually, here's a comment from Sid. You can also measure voltages on the ground plane with a high bandwidth differential probe, especially if it is a bus with ground return path problems.
Yep, you can do that. So that comment. Any comment on that, Hany? That seems like a
thank you guys. Thanks a lot.
Yeah.
Okay, good. Question from Song. Does EMI Lab vary different memory algorithm and data frequency?
That's the nice thing about the virtual world. Actually, you can do, as I mentioned in one of the examples, you can do stuff that you can never do in real life, which is, let's say, shutting down some address nets and turning them on again. Something you can never do in real life, but you do it for debug purposes only. Now, I think if you're talking about the current profile is measured, the reason I actually use the measured current profile for SSO noise emission is that use the actual maximum activity on the GPU for the memory. And then we can really extract the worst case current profile out of this activity, of the actual physical chip. On its different corners, and therefore now we can inject it into simulation, actually have even a better immunity of your PCB decoupling scheme using the physical maximum activity of your memory controller as an example. But on the virtual world, nothing can prevent you from selecting frequency, from selecting a lot of stuff that even you can never do in real life. There is no restrictions on the virtual field.
Okay, thank you, Hany. And a follow-up question from Song. Can phase differential, 90 degrees, EMI cancellation be calculated and therefore recommended on PC trace layout in the simulation stage?
Actually, that's a very good question. For momentum method as an example, if you have differential traces, you can really control the excitation for your radiation problem. So say you can put on one of the traces a signal that is 1 and the other one would be, let's say, 180 degree or 175 or even 90, 95. So you can really excite the problem you wish at the ports of your momentum. And that's the thing, yes. So based on that, your sources are controllable. Therefore, you can really compute what is the required phase cancellation from the simulation by controlling these sources. So you have now to try it. Most probably you can sweep the, let's say, the phase cancellation between the different signals till reach a point that you have the minimum type of radiation. And that's something very nice, by the way, in momentum, that you don't need to rerun the simulation. You only rerun the post-processing. So go to the post-processing window, change excitation as you wish. Let's say only one differential pair, you change it from 1 to, and the phase, you can change the phase from 180, 175, 160, whatever, to a point that you've seen minimum type of emission based on the cancellation that you would like to put as a phase cancellation.
Thanks, Hany, and thank you very much for this great discussion. It looks like that's all of the time that we have for questions today, and we will follow up with the rest of the questions by email. But before we close, Hany, I'd like to get some closing comments from you.
Yeah, I'm just hoping you guys really can try, instead of the stressful time in the anechoic chamber, just like providing here a tool that can help everybody from EMI to do what-if analysis. We know that it's going to be very difficult to imitate the real system. However, we're trying, as usual, to break a problem into simple problems or into simple structures and be able to compare in between and understand the trend using our simulation engines. Unfortunately, no single method can do it all. As everybody maybe have seen already, we cannot only use moment method alone. We cannot only use frequency domain technique alone. We cannot use time domain techniques alone. We have to use a combination of stuff. Even our transient convolution engine is needed, as an example, to compute the common mode between differential pairs. As an example for HDMI differential traces, how do you know that the amount of rise-fall mismatch may be enough not to produce a problem, or maybe at the limit to produce an EMI problem. So we have to use different tools in our hand, including the hardware tools such as near-field scanning. Still, the 3-meter, 10-meter, 5-meter chambers are required, and with this virtual lab altogether, method, finite element, finite difference time domain are all needed beside the convolution engine to be able to get into a good risk assessment.
Thank you for your presentation today. As we wrap up today's presentation, remember that we will email you a link when the on-demand version and the PDF slides are posted on our website. You're also invited to register for our other webcasts. And if you're interested in power amplifiers, we have the perfect series for you. It's the RF Power Amplifier Design Series. If you can go to that slide, Bridget. We have 2 dates, March 1 and April 5th, so don't forget to register for those. If you're viewing the on-demand version of this webcast and have a question about any of the material, you can go ahead and email Hany directly at Hany_Fahmy@agilent.com. I'd also like to remind on-demand viewers to complete the webcast survey that will automatically launch at the end of the webcast. Again, for attending today's event, Introduction to EMI/EMC Challenges and Their Solutions, brought to you by Agilent ESOF. The copyrighted presentation material is owned by Agilent Technologies. For a current schedule of live and on-demand events, please visit us at www.agilent.com/find/events. And you can see URLs on the screen for a look at our recorded webcast. I'm Karina. Thank you for joining us and have a great day.